Okay, hello. Can everyone hear me? Hi. Today we have the honor to have Marisa Brienza as a speaker, and I will briefly give a short bio of our speaker. She is currently a postdoc researcher at the University of Bologna, and she's working with Professor Vazza on the impact of old radioplasma from AGN on the non-thermal energy of galaxy clusters. She focuses then mainly on radio galaxies and their evolution, and particular attention is given to the life cycle of jets and their interaction with their surrounding environment. Before that, she is part, sorry, before I talk to that, she's a part of the LOFAR survey key science project since 2014 and has been using several radio telescopes around the globe, such as LOFAR, JVLA, and UGMRT. And she's currently contributing to the scientific exploitation of the instrument to its commissioning, as well as to the development of the Italian LOFAR computing infrastructure. Apologies, I don't have the information of prior PhD work, but please go ahead. You can mention that, and we can give the stage to our speaker. Thank you. Thank you very much.
Okay, thanks a lot. So I will share my screen. Yeah. Let me know, please. Can you see in full screen mode?
Yes, we can see it. Yes.
In full screen, or do you see my desk?
No, we can also see the slides on the left.
I'm sorry, then let's try now. Now?
Now, yeah, now it's done.
Okay, great. Then I'll start. Thanks a lot for the introduction and for having me here today, of course. So going back to my what I did prior of this, so I graduated at the University of Bologna in Italy, and then I moved to the Netherlands for my PhD, where I worked with Raffaella Morganti at Astron and the Kaptein Institute in Groningen. And then I moved back here in Italy, in Bologna. First, I was working as a postdoc at the Institute for Radioastronomy, and now, as you said, at the University of Bologna, working with Franco. So yeah, today I will give you a very personal, of course, overview of my field of research, which is the AGN life cycle and feedback. And especially, I will give you, let's say, an overview of the progresses that we are making in this field from using low frequency radio observations. Let me close it here. Okay. So let me start very, very briefly from scratch here. So we know that most galaxies in the universe host a supermassive black hole at their center. And these supermassive black holes can reach masses up to millions of solar masses. And because of their enormous gravitational force, they attract all the gas, all the material that surrounds them. And in this process, they release a large amount of energy in the form of radiation, and but not only. And during these phases, we refer to these black holes as active, and in particular, we name these systems active galactic nuclei, in short, AGN. And some AGN, during the black hole's accretion, also develop jets of relativistic particles and magnetic fields, which expand in the surrounding medium and can either be confined within the stellar body of the host galaxy, but can also travel much beyond, up to hundreds of kiloparsec scales or even megaparsec scales. And because these are charged particles moving in magnetic fields, they produce and they release synchrotron radiation, which is mostly visible in the radio band, and they produce a power law spectrum of the form you can see here. So now I showed you a simulation of AGN jets Now I'm showing you a real image of a very famous system, which is MHz-0735. This is a very powerful AGN sitting at the center of a very massive cluster. And in red and green here you can see the radio emission from the jets. And you can really appreciate how the jets are inflating these bubbles, these lobes in the surrounding medium. And what is this surrounding medium? So the blue colors here is the X-ray emission coming from the diffuse plasma, which is diffuse gas, which is filling the intracluster or intragroup medium. And if you just look at the X-ray without the radio overlaid, you can really appreciate clearly that there are some cavities, so there are some darker regions, so less X-ray emission. And these are called cavities and are regions which are coincident with the AGN jets, AGN lobes, really suggesting clearly that the jets are displacing the material they encounter during their journey. And this, let's say, this action creates a really important impact on the surrounding medium, which is called, let's say, mechanical feedback, which is not to be confused with the radiative feedback, which is the feedback an AGN can produce due to its radiation. And beyond these cavities, AGN jets can also drive shocks, sound waves. They can induce turbulence in the medium, and they can also uplift the lowest entropy and metal-enriched gas, which is located at the center of the galaxy upwards. So all these, let's say, processes are to be considered mechanical feedback. And why do we care about mechanical feedback? We care because we think and this has a real impact on galaxy evolution. And in particular, in a quantitative way, I think this is one of the most famous and clearest plot where you can see quantify a bit the impact, the energetic impact of AGN jets on the surrounding environment. So here on the y-axis, you have the power of the bubble or of the cavity, computed as the work made by the jets to inflate the cavity, or actually to inflate the lobe, divided by the age of the lobe. And on the x-axis, you can see the X-ray luminosity. You can see a clearly correlation here, spanning over almost 6 orders of magnitude. This is really telling us that from an energetic point of view, these bubbles, these AGN bubbles, are really able to stop the cooling of the surrounding medium in a variety of systems, from very massive clusters down to groups and even individual ellipticals. Again, this is very important. Why? Because we think that this energy, which gets released by the AGN, is a really necessary ingredient to explain galaxy evolution throughout the universe. And in particular, here again, it's another famous plot by Croton and collaborators in 2016, where you can see the mass function of galaxies. In blue, you can see observational points, and in black, the lines of the simulation. You can see that without the AGN jets as an ingredient in the simulation, the simulation overpredict largely the number of massive galaxies in the universe. So this energetic this energy is from the AGN jets is really necessary. And another ingredient, which is important in all this scenario is the life cycle of the AGN jets. And when I talk about life cycle, I mean the fact that AGN jets are actually a recurrent phenomenon in the lifetime of a galaxy. So they are not always switched on, but there can be periods where they're on and periods where they are off. And usually we refer to the life cycle as the, let's say, path which is followed by a jet, first being very compact and confined within the host galaxy, then expanding beyond the host galaxy. This not always happens, but can happen. And then after a certain amount of time, these jets switch off and we have the so-called remnant phase, remnant source, where the jets are off, so we don't see them anymore. We are only left with some remnant lobes, that is the AGN lobes, which are fading away. They are expanding in the surrounding medium and radiating away their leftover energy. After this phase, we can have a new phase of activity, giving rise to the so-called restarted sources. And these restarted sources are the best evidence of this recurrent AGN jet activity. The most famous classes, let's say, are the double-double radio galaxies, where we can see at the same time some compact double sources, some compact jets, and together with another pair of lobes, which extend on much larger scales, and represent, are interpreted as evidence of the previous AGN outburst. But there are also other morphologies, actually. In the bottom, you can see a couple of examples where you have compact jets in the inner regions, and then not really two separate double lobes, but on large scales, you have just some very amorphous and diffuse emission. And the interesting thing of these sources, useful actually, is that we can use them to constrain the duty cycle of the jet activity through the study of their radio spectrum, as I will tell you later in more detail. Other evidence of this recurrency comes from observations of multiple pairs of cavities in galaxy clusters and groups. And these also are interpreted as evidence of AGN repeated outbursts, are observed in both very massive systems and smaller ones, as shown here, just a couple of examples. And also in these cases, you can get a first order estimate of the AGN duty cycle, of the jet duty cycle. In this case, through dynamical considerations on the bubble rise in the surrounding medium. In particular, we can assume that the bubble is located, we can measure that the bubble is located at a certain distance from the center, and we can assume a velocity of this bubble equal to the sound speed, for example, as a maximum limit, but also buoyancy, and we derive an age. And a duty cycle if we have multiple cavities. Useless to say that having a clear idea of this duty cycle, of the timescales of this AGN jet activity, is essential also for quantifying the feedback we were talking about before. So in all these, let's say, very nice qualitative scenario, there are actually, which flows very nicely, there are actually a lot of things that we still don't properly understand, or we don't understand at all. For example, we have an overall idea of the time scale activity of the jets, but we don't know the details of how these relate to the host galaxy and to the environment. We don't know exactly how this AGN jet plasma interacts with the surrounding medium, and the physical mechanisms that convert the bubble's power into heat is still very much debated. Also, we don't know exactly how these bubbles evolve on long time scales, because it's really difficult to follow them. And also, for example, the role of magnetic fields and viscosities in their mixing with the surrounding medium. So a lot of things still to understand. And of course, the advent of new generation instruments in the radio band, of course, like ASCAP, MIRCAT, LOFAR, MWA, but also the updated receivers on the Westerbork and GMRT and VLA are really revolutionizing the way we look at these sources, and are really pushing forward their study with their very much enhanced sensitivity and resolution. In particular, low frequencies are especially important. With low frequency, I mean, let's say below 1 gigahertz. And why is that? Because they're very sensitive. They're very ideal to detect the oldest populations of emitting particles. And the reason for this is shown in this plot, which is the spectrum of a radio source, which is aging with time. So as I said before at the beginning, the synchrotron spectrum is a simple power law, and then it steepens and gets curved with time. The more time passes, the more the spectrum gets curved. This is because the most energetic particles, which are the particles emitting at the highest frequency, lose time much more quickly than the low energy particles. And this translates in this very pronounced curvature with time. This means that this means two things. On one hand, it means that observing the sky at low frequency means we are able to detect the emission of the oldest population of particles for a much longer time. And it also means that there is a direct relation between the curvature of the spectrum and the age of the plasma which is producing that spectrum. And in particular, the steeper, the more curved spectra are associated to very old, to older particles, while flatter spectra are associated to younger particles. And here, just a brief mention to the LOFAR 2-meter sky survey, LOTS, which is a survey aiming at covering the entire northern sky at 144 megahertz at 6-second resolution and about 0.1 millijansky per beam. I'm mentioning these among others, which are also ongoing with other telescopes, because first of all, of the low frequency, which is used, but also because of the large field of view, which is already available. And this is really important, especially to look for and to study rare sources like, for example, AGN jets in different phases of their evolution. And the power of this survey is, together with the low frequency and the very high sensitivity, also the very rich UV coverage, which allows us at the same time to have quite high resolution images, so to be sensitive to the fine details of these AGN, but also sensitivity to large scale structures, thanks to a very rich core of antennas in the central regions of the array. So in this case, thanks to this, we can clearly observe also very extended diffuse emission. And one of the classes of sources that are really benefiting a lot from these instrument updates is the class of remnant radio galaxies. So remnant radio galaxies, as I said before, represent the last evolutionary phase of the jets, when the jets actually have switched off, so we don't see them anymore. We just see some lobes which are radiating away their energy and expanding into the surrounding medium. And these sources are known since many decades, but have remained very elusive for a lot of time, just mainly because of observational limitations. And However, they are really important for a number of reasons. First of all, they allow us to understand how the plasma evolves with time after the jet switch off, and also to constrain the length of the duration of the jet activity. Here now I'm showing you a very classical example, which is the source B20924 plus 30, which I think summarizes all the main properties which we think are typical of a remnant radio galaxy, and which are actually also used then to select these sources, to identify these sources from large field of views. And this is these are a relaxed morphology without compact features, like we don't see cores or jets or hotspots, and they have very curved or steep spectral spectra with spectral indexes typically higher than 1.2. However, as I said, the new generation instruments is doing a lot for these sources. We are discovering many more. And here I'm just showing you a short list of some recent examples which have been detected and studied actually thanks to a variety of instruments, which is also very nice. And together with these new discoveries, we are also learning more about these objects. For example, here, I'm showing you a specific source which we studied a few years ago, where we detected a very curved spectrum, which we classified as a remnant based on very curved spectrum. But we also noticed that the spectral index at low frequency, so below 1 gigahertz more or less, was not very steep. So this source, for example, would have been missed by a classical selection criteria based on steep spectrum at low frequency. Moreover, using very sensitive observations at high resolution, we detected the presence of a very faint core in the inner region of the galaxy with very low core prominence. And the core prominence is defined as the ratio between the flux density of the core and the total emission of the source. And this was also a bit unexpected for a remnant radio galaxy. But nicely now we are getting more and more samples of these sources, and we are actually in the last years we are actually understanding that these features are not that unusual, that unique. For example, here you can see an histogram on the top showing the spectral index distribution of a sample of remnant sources selected by Mahatma and collaborators, where you can see that also remnant sources can have actually spectral indices at low frequency, not so steep. And this is actually expected also from a theoretical point of view. In the bottom of the slide, you can see a model showing the same source counts versus spectral index, and here you can see that there is indeed a high spectral index tail of remnant radio galaxies in blue, but there are also remnant radio galaxies that have flatter spectral indices, and these are probably just the youngest tail of the entire remnant population. Also about the cores, this is something quite interesting. Even in remnants where we see very steep extended emission and curved emission, we actually detect very often, not always, but we detect some cores when we have available very sensitive observations at high resolution. These cores are usually very faint, so nothing to do with a real active core, let's say, of a typical active galaxy. But there are some cores. So this means that while the large-scale emission is and the large-scale jets are probably switched off, there is still some ongoing activity in the nucleus. And this may be consistent, for example, with some recent results from Sabater and collaborators, showing that the most massive galaxies always show some level of radio emission. And here you can see a plot showing the fraction of radio-loud AGN versus their luminosity, and the different curves and different colors show the different mass beams of the host galaxy. And you can appreciate that for the highest mass beams, so the most massive galaxies, on one hand, host the most powerful AGN, and on the other hand, they reach fractions of radio-loud AGN almost equal to 100%. So this means that at least some faint radio emission is always present in these systems. So another important angle, let's say, for the study of remnant radio galaxies is through their statistics. It is important to define, to measure the fraction of remnant radio galaxies with respect to the active radio galaxy population in order to give constraints to models describing the radio galaxy evolution, so how the plasma really, the jets evolve in the surrounding medium. And thanks to these observational studies that I was mentioning also before, that these samples that we are collecting nowadays, we know that more or less, depending on the selection criteria on the instrument used, more or less we get a fraction between 5 and 15 or 20 maybe of remnants with respect to their parent population. And this can give us some constraints. For example, if you look at the left panels, you can see that according to models, if there was no expansion at all after the jet switch off, we would expect a much larger fraction of steep spectral index remnants, about 40%. Instead, by including some expansion, the fraction becomes much more compatible with observations. And just another example on the right, we can use the fraction of remnants to constrain the typical age of the AGN jets. In the top panel, for example, you can see a model that assumes that all sources live for the same amount of time, and this would imply a fraction of remnant radio galaxies which is very low. Instead, if we assume a power law distribution for the ages of AGN jets, then the fraction of remnants becomes much more compatible with observations. And these are, I'm not going into details, but just to give you a feeling for what we can do with this. So it becomes even more important to expand out the study of these sources to larger and larger samples, and LOTS is actually a very good opportunity for doing this at the moment. But of course we cannot do it by hand like we did almost in these previous studies. We need to find automatic ways to do it. So there are machine learning techniques there based on morphological classification. And here I'm just showing a couple of attempts we are trying on LOTS. One is based on simple pixel statistics, which is picking up sources with very uniform distribution, surface brightness distribution, sorry. And another one led by Raphael Mostert based on self-organized maps. And the aim is really to select finally tens or even hundreds of good remnant candidates. So I was saying before that remnants can also be used to constrain the age of the jet activity, and this is through the use of the radio spectrum. So as I showed at the beginning, the spectrum becomes steeper and steeper, actually more curved and curved with time. So there is almost a direct relation between the age of the plasma and of the source and the age of the and the shape of the spectrum. And in particular, you can see here the relation between T and the break frequency, which is the frequency at which the spectrum starts to steepen. And of course, a big role in this equation is played by magnetic field, which is the main driver of the particles cooling. So by fitting the spectrum with radiative aging models, we can actually constrain the age of the plasma, and we can do it on the integrated spectrum of the source. This means one spectrum per source. Or if we are lucky enough to have enough maps at different frequencies with a similar resolution and sensitivity, we can even study the spectral age of the plasma in different regions of the source. And this, you can see an example of this on the right, where each pixel here it's colored based on the age. And with this technique, we can really constrain the time scale of the jet activity. And in particular, with the few sources where we have done this, we have seen that the jets are active for, depending on the systems, from a few tens of mega years up to a few hundreds of mega years. And this becomes even more interesting when this method, when it is applied to restarted radio galaxies. So when we are able to constrain the age of both the outer lobes, which are related to a previous phase of AGN activity, and the ongoing activity, the ongoing jets. In this case, we can really study and get some constraints of the duty cycle of the jets, and to study the ratio between the inactive phase and the active phase. And here I'm showing just two examples that we have recently studied, 3C388 and MS0735, which is actually the source I was showing at the beginning, where we have constrained the duty cycle to be very fast, with let's say a fraction of about 30%, with the inactive phase being about 30% of the active phase, so very short quiescent phases in between jet activity. But of course, this is only possible for a few sources where we have a collection of multi-frequency data. And if we don't have all this frequency available, we can still use the spectral index information. We can use the resolved spectral index maps. So we can study how the spectral index varies across a source. And here you can see two different cases, an FR1 radio galaxy and an FR2 radio galaxies, which are where you can see that the gradient of the spectral index is different. In particular, in FR1 radio galaxies, which are core brightened, so the acceleration of the particles happens in the central regions. We have a flatter spectral index in the inner part, and then a steepening moving outwards. On the contrary, FR2 radio galaxies are edge brightened, so the acceleration happens at the edges in the hotspots, and so in these regions we have flatter spectra, which means younger electrons. And now we are at the stage where we can start doing this kind of studies also on and searches also on large samples. And here, for example, this work by Raffaella Morganti, published last year, obtained by combining LOFAR and apertive data on the Lockman Hall field. Here, it was possible to study in a systematic way the spectral properties of all the extended radio galaxies in the field, so of a significant amount of galaxies. And actually, this allowed also to select some remnants and some restarted sources. So this is a further method that, of course, this doesn't give you the a precise number on the age, but it's a very powerful method to study the relative age and to select sources. And finally, in the last part of my talk, I would like to concentrate a bit on the interaction, on the progresses that we are making in studying the interaction between this AGN remnant plasma and the surrounding environment. Because as I said, with low frequency radio observations, we are able to track this remnant plasma up to very large distances and ages. And so we are detecting remnant plasma even in sources which were very well known at higher frequency up to a few years ago. Here I'm showing you just 3 examples of very well-known sources, where on the left you have the radio emission at higher frequency, how we were seeing it before, let's say, the advent of new generation instruments. And on the right, you can see how much more of emission we can see now with LOFAR in this specific case. But there are beautiful cases also with other detected nowadays with other instruments. And why this is important, again, it's useful to follow the interaction between this remnant plasma and the surrounding environment to understand better feedback. But also, actually, there is another reason, which is to understand how this plasma distributes into the environment and whether it can really be useful for the formation of diffuse radio sources in galaxy clusters. So these diffuse sources, which are usually classified as relics, halos, and mini halos, are not associated to specific galaxies, but they are just diffuse and extended up to megaparsec scales, and they're thought to be created due to the dynamics of the system, so because of shocks or induced turbulence. I won't enter into details on this. I'll just say that these AGN fossil electrons, this remnant plasma from AGN, may play a really important role in seeding and creating this system. So this is another reason why we want to understand how this plasma disperses into the medium. And in particular, I will focus here on 2 sources, which I think are very representative, let's say, of this. One is NGC 507, which I also briefly showed you before. This is a well-known source, a well-known galaxy group of about 6 in 10 to the 13 solar masses located in the nearby universe. And up to very recently, we knew that associated to the central galaxy NGC 507, there was a low-power remnant radio galaxy, which is the double lobes that you can see at the very center. Now, with LOFAR observations, we have actually detected a lot more of extended emission, which you can see mainly on the bottom right part of the image. And this is clearly connected with the main double lobes, and we interpret it as AGN remnant emission from a previous AGN outburst. And very nicely, this emission is diffuse and very filamentary, and in particular, there is a main filament in the south, which has an S shape, and is really following an X-ray discontinuity that was actually even previously detected. So what we can do with this system, we have studied the spectral age, as I mentioned before. So through radiative aging modeling, we have computed that the inner double lobes have an age of about 150 megayears, while the remnant plasma newly detected on the right has about 300 megayears. We don't really recognize any clear trend or flattening, so no signs of compression ongoing. We think that this is just plasma, which is mainly aging. If we look at the X-ray now, to understand what is happening to this AGN remnant plasma, we can detect a very peculiar spiral morphology. and in two very clear discontinuities, one on the east side and one on the south. Here you see the X-ray map on the left, the residual map after beta model subtraction, and on the right, the X-ray map filtered with a GGM filter, where all these features are really clear. And this spiral morphology is interpreted as a sloshing motions, that is, large-scale motions of the gas within the group, which are initiated by some perturber system, which is passing close by. And so it's this is telling us that the group is dynamically, let's say, active. And in the south, you can see no, sorry, not in the south, in the bottom, you can see the profiles that we derived in the direction of the discontinuities. In particular, we see a drop in surface brightness in correspondence of the discontinuities, and these correspond to a slight temperature increase, which is typical of cold fronts. And here, quickly, you can also see the spectra, the X-ray spectral maps, where you can see the distribution of the main properties of the gas in the system, which are very much symmetrical and also recall a spiral distribution. So overall, in this system, by combining low frequency data and X-ray data, we understood that this remnant AGN plasma is getting transported by sloshing motions, and this plasma is still not really mixed with the intragroup medium, but is just being, let's say, diffused all around. There are not so many, there are a few systems now in the literature where galaxy groups, I mean, where we see cold fronts and also spiral structures, but this is, I think, the first or the best, I don't know, example where we really see with high resolution and sensitivity, both in radio and in the X-ray, clear more co-spatiality, let's say, between the X-ray and radio features, and we can understand what is happening to this plasma. So overall, this plasma on longer time scale will reach probably also even further distances with respect to the center, and in the end will represent a pool of mildly energized particles which will permeate the system. And yeah, here another system, another group, which is very impressive, I think. And where we see actually, it's probably the best example where we can follow the evolution of these AGN bubbles on large time scales and large spatial scales also, is this NEST 2047, which we have recently studied. And this is quite a small group with only about 20 galaxies. At the center, there is a BCG, which is repeatedly producing AGN bubbles. And these AGN bubbles are observed for the first time on such long time scales. And we see exactly how they develop, how they change morphology, and how this plasma, this AGN remnant plasma, gets let's say distributed throughout the system. We see multiple radiolobes, actually multiple pairs of radiolobes. The more, of course, we move in the outskirts, the more the oldest the bubbles are. And we see a lot of filamentary emission, which is tracing really the presence of plasma and magnetic fields. And for this for these systems, we obtained observations both in HPA and in LBA with LOFAR, that is at 144 MHz and 54 MHz. And by combining them, we could also investigate the spectral index distribution. In particular, you can see that the flat spectral index is in the center. So this is corresponding to the active lobes. And the more we go away, the more the spectrum gets steeper. And there is also a lot of diffuse emission with very steep spectral index. So this is consistent with particles aging, moving outwards. Actually, there is a bit of flattening in the main filament in the north, which we think might be related to some possible compression. And for this system, we also we accessed the Rosita observations, which are in the X band, which allowed us to characterize roughly the gas properties surrounding these bubbles. And here you can see some basic properties that we derive, like temperature of about 2 keV and mass consistent with a galaxy group. So what are these shapes that we are observing in this very spectacular system? We think that we are really observing the evolution of the bubbles in the surrounding medium. Indeed, when this bubble starts rising in the AGN, we think that, simulations and theory shows that the pressure gradient present around the bubble transforms its roundish shape, more or less, into a ring structure, into a toroidal structure. This happens also on Earth in some cases, for example, smoke rings, explosions, and these very nice volcano eruptions. In the astrophysical context, this is much more rare. The only case we knew before this was MHz-7, where we also detected a mushroom, let's say, shape feature, which was interpreted as a bubble evolving into the surrounding medium. In this case, with NEST 2047, we think that we are observing actually a much more advanced phase with respect to MHz-7. And in particular, we are seeing the system like AGN. So the main filament in the north, we think that could be interpreted as a ring as in AGN, and the overall emission represents, a bubble expanding in the surrounding medium. We estimated an age for this bubble of about 200-300 mega years, and we found that actually the bubble power is consistent with the luminosity of the X-ray luminosity. So it seems that AGN feedback can work nicely also in this system, and it can be effective even without a complete mixing of the AGN remnant plasma with the surrounding gas. Something also which is impressive is the stability of these filaments and these structures. Indeed, after so many years, we would expect some instabilities to develop, which would in turn destroy these filaments. But apparently this is still not happening, and we think that magnetic fields may play a role in preventing the destruction of these features. And we think this because the Alphen scale, which we computed, is more or less of the size, equal to the size of the filament's width. So this might actually give us a hint. And of course, there is a lot more to understand about this object, which is very complicated, but is surely teaching us something more about how the plasma on large time scales, the remnant plasma can evolve and can mix or not mix with the surrounding environment. Of course, in all this, we cannot exclude that there might be also some weak shock waves passing through the system and shaping the morphology due to, for example, some group dynamics or the repeated AGN activity producing weak shocks. But this is something we will address at a later point. So with this, I come to my conclusions, which I kept very short. I think the main message I would like to make here is really that we have entered actually a new era where we can now study with much detailed remnant and the remnant AGN plasma, and this gives us the possibility to produce new large samples of sources on different phases of the AGN life cycle, so to constrain better these phases of the AGN life cycle, to constrain the duty cycle, but also to understand in more detail the interaction between the remnant AGN plasma and the surrounding medium, to understand better feedback. And of course, simulations and modeling are further required to understand all this in a better detail. But I think observations are giving us a lot to work on. So that's very nice. Thanks a lot for your attention.
Well, that was great. Many thanks, Marisa, for this very interesting talk and this thorough and detailed trip for radio galaxy morphology, their life cycle ages and everything. I hope everyone is as excited as I am and that has lots of questions. So please be my guest. If you have any questions, just raise your hand or just unmute and unmute. And
happy to answer your questions or curiosities, of course. Thanks a lot.
Thank you. So any questions, or you can just type it, or maybe I can just start and kick in with something easy and maybe people can join. Where you were talking about the automatic selection of the morphology of the remnant galaxies. So is this only based on morphology, or is there anything else behind it? Are you checking spectral index or any other parameters? So what is the basis of this automatic selection, let's say?
So this is a very good question. So the thing is that we're working, that selection was referred to our attempt to select remnants in lots. So the LOFAR sky survey. And the problem is that we don't really have complementary data which are at a different frequency, which are deep enough and sensitive enough to perform a spectral selection. So at the moment we are just a bit constrained by these, and we are only applying morphological criteria. The spectra, so to select the first, let's say, sample of candidates, and then for sure we will need to complement this with higher frequencies, but it's a bit difficult as a starting point just because of the absence of any higher frequency survey. So, but I mean, this is something that can be addressed with surveys which have from the start multi-frequency data. For example, I'm thinking of MIGHTY, which has also the complementary GMRT data. So that's a very, when you have specific fields where you have complementary frequency, that's a very good strategy to combine morphology and spectrum. In this case, in lots, it's very difficult, unfortunately.
Oh, yeah, sounds good. Yeah, so yeah, thank you. Yeah, so I saw a question in the chat. Okay, so there's a question from Bena Hugo. Okay, can one not use optical lines to identify a host AGN, for instance? I mean, yeah, but this is in the optical side. Sorry, yeah.
Yeah, no, that's fine. I mean, yeah, AGN can be also selected based on their optical lines, but just remember that not all radio AGN, so not all radio galaxies have optical lines, because that's depend on the way the optical lines depend on the way the nucleus of the AGN is working, let's say, in a simple way. And so, yeah, not all radio galaxies have optical lines. And actually, remnant radio galaxies are not really expected to have optical lines. I'm not sure whether I answered this.
Yes. So, any other questions?
Yes.
Yes, thank you. So one more from Tracy Clark, thank you. Are you able to detect or place interesting limits on the polarization properties of the emission you are seeing for some of these fantastic new features?
Yeah, thanks. I still don't have polarization information on these. I mean, there is some work ongoing. for the next source, so the last one I presented, we are analyzing now multi-frequency dataset obtained with GEMRT and VLA, and we have I can give you some spoilers. So with the VLA at 1.4 gigahertz, we see some polarization in the main filament in the north. But that's the only, this is still work, and I still didn't finish to reduce the data, and this is just for the brightest features. Some features are very low surface brightness, so it's also a bit difficult to go in that direction, but that's for sure a very interesting point, which we should investigate further in not only in that source, but in the others. I agree. Yeah, thanks.
Many thanks. Are there any other questions I can transfer to our speaker? To be honest, I also have one more.
Please.
If in case we have one, for the very lovely system of NGC 507 with a sloshing, I found that very interesting. May I ask whether, because I see that the remnant emission was towards the southwest side of the jet, whether the sloshing has also affected the way that the second AGN has been, has it changed the orientation in a way of the jet, of the radio jet, or of the emission? Because I mean, from what it seemed to me, it was in a way one-sided. Of course, lots of things are going on there with the sloshing and everything, but I just wanted to use it as an opportunity to discuss a bit more about this system.
Yeah, for sure. Let me take the picture.
Yep.
One
Thank
second.
you. Yes.
Yeah. So here, so you mean, so this, do you see my cursor? I don't know. No. Do you see my mouse? Do you see my
Yes,
mouse?
I can see it. Yes, yes.
Okay.
Sorry, I can see it. Yes.
So you are saying that this remnant plasma.
Sorry, I cannot see it. Sorry, my bad.
No, okay.
My mouth.
The new, let's say the newly detected emission on the bottom right of the image is probably following these large scale motions, but I'm not sure I got your question. Can you repeat, please?
Whether, yes, whether after slosh, so it was the, as I understood, the first phase of the jet, then it was the sloshing that
yes,
has affected all this, but whether what the next, let's say, AGN that we see has been affected by this sloshing, so maybe this was in a way changed its line of sight, or whether all this is at the same, let's say.
Okay, yeah. So the inner double, you mean?
Exactly, yes.
This is a good point. I mean, the inner double looks, let's say, also a bit. The shape of the lobes look a bit bent. For example, if you see on the western side, for example, there is what I call a secondary X-ray peak. That is a bump of X-ray emission, which is actually coincident with some with this bend towards north of the radio jet, if you can see.
Yes.
So here, for example, there is a suggestion that there is interaction between the AGN plasma and the surrounding X-ray emission, so some compression ongoing. So for sure, the inner double is influenced and is interacting with the surrounding medium. But around about the sloshing itself, I'm not sure that it has some influence. I need to think more about it, but it's a good question.
Okay, yeah, thank you. In the meantime, one more question. I hope you're not too tired, Marisa.
No.
From Paul Fallon, is there understanding of how magnetic fields impact the filaments and jets?
Okay, very general question.
Yeah.
I hope I mean, not general, but very huge question. So what I can say is that I don't know, talking about filaments, if you are talking about these filaments that we start to observe, for sure these are related to the magnetic properties of both the AGN remnant, but also the properties, the magnetic properties of the surrounding gas. And this is also why we want to study them, because it's like having a probe of the external gas, which we would not have otherwise. In the case of NES, as I showed you, the alphen, where is it? Let me go 1 second. Yeah, the alphen scale, oops. The alphen scale here, for example, is 5 to 15 kiloparsec. So the alphen scale is the scale under which the magnetic field starts to play a role in the hydrodynamics, let's say. So it's the magneto-hydrodynamic regime starts up under this scale. So the fact that we see these filaments and they have exactly this width, more or less, it's suggestive of the fact that magnetic fields, yes, play a role. And in impact on the overall AGN jets, yeah, I'm not sure what to reply to this. I'm sure, I mean, jets are driven by magnetic fields, so particles are collimated around the black hole by magnetic fields. So yes.
Yeah. Thank you. And one more question from Bernard Farnarov. Thank you very much. The most massive galaxies are always on. But we also see it from recent studies, indeed. Do you see different statistics of restarted sources and remnants for these galaxies?
That's a very, very good question. Thanks. We are still not at that point. I mean, we still don't have enough statistics on remnants and restarted to answer this question. But that would be a real good thing to address. That's the hope, let's say, with larger samples. Yeah.
Okay, great. So, are there any questions? So, if there aren't any questions, let's actually thank our speaker again. It has been a very interesting talk. Many thanks, Marisa. Many thanks everyone for attending. And
thanks a lot to everyone and for attending, and to the organizers for inviting me, of course.
Many thanks too. Okay, bye.
Bye-bye.